Oh, that's it. Okay. So good morning. My name is Jonas Keller from PTB in Germany, and I want to talk about our recent results regarding the reduction of trap-induced systematic uncertainties. These were done in our effort to build a multi-ion optical clock. But before I begin, I want to stress, of course, the individual results similarly apply to single ion clocks. So let me start by addressing why we want to use multiple ions. Of course, single ions are known for their ability to achieve low systematic uncertainties, but the major drawback is the high level of quantum projection noise when interrogating a single particle. And so that means that in order to average down to a 10 to the minus 18 uncertainty, about a week of averaging is necessary with a single ion. And we want to improve on that by doing part of this averaging in parallel. And so, for example, by increasing the ion number to 100, we could already reduce this time to about 1 hour. An additional advantage is that with each interrogation, we get more spectroscopic information out of the system, and that means we can lock the local oscillator to the atomic signal with a higher bandwidth, and that strongly reduces the requirements on the intrinsic local oscillator instability. And finally, for clocks limited by local oscillator noise, there are several proposals to further gain from a higher number of ions by using correlated ensembles or by doing cascaded interrogations to be able to interrogate at the optimum interrogation time without the risk of cycle slips. So today, this is what we envision. We want to trap Coulomb crystals on the order of 10 ions each, and then do further scaling by trap segmentation. And in our lab, we're implementing this with indium ions. One of the reasons being that with the low sensitivity of the indium clock transition to the electric quadrupole shift, it's insensitive to the unavoidable electric field gradients inside such Coulomb crystals. This also goes for the aluminum clock transition or the ytterbium octopole transition, so those would be suitable candidates for this approach as well. Indium also has a low sensitivity to black body radiation and to the second order Zeeman shift. And what's a really nice feature in terms of scalability, we have this 360 kilohertz intercombination line, which we can use for direct detection, which means we don't have to develop quantum logic protocols that work in 10 ion crystals. Also, we could, if necessary, use this for a Doppler cooling stage that would basically get us to the ground state of the trap. But we don't want to solely rely on this narrow transition for cooling, and so we additionally sympathetically cool with ytterbium, where we have this 20 megahertz dipole transition available. So, as I said, I want to talk about systematic uncertainties, and looking at the best published error budgets of single ion clocks, it's apparent that the major contributions here are all related to the ion trap. And so what I want to talk about today is our efforts to reduce these contributions both by trap design considerations and by careful determination of the underlying effects. And so the talk consists of 3 parts. I first want to talk about secular motion. Then I want to present some results regarding micromotion determination. And finally, I want to talk about the black body shift due to heating of the trap. So here's an example of a 10 ion crystal with 9 indium clock ions and 1 ytterbium cooling ion. These are the radial mode eigenvectors. And if we manage to cool all of those modes to the Doppler temperature of ytterbium, the indium ions would experience a 1 times 10 to the minus 18 second order Doppler shift from secular motion. And so we need a low temperature uncertainty for all motional modes. And the easiest way to achieve this would be to ensure that we can reach the Doppler limit for all of them, which is basically saying we need high cooling rates compared to the external heating rates. And this is particularly a concern for this in-phase mode, which is most prone to heating due to homogeneous fluctuating external electric fields. And so there are 2 design considerations in our trap to reduce this effect. First of all, since all heating processes scale with some inverse power of the ion to electrode distance, we've chosen rather large trap dimensions. And secondly, since we don't need fast shuttling operations, we can afford to low-pass filter all of our DC voltages directly next to the trapping region at 100 hertz. So in order to see how those measures worked, we cooled a single ytterbium ion to the ground state and used it to probe the field. And we saw in a prototype trap heating rates below 2 phonons a second, for trap frequencies around 500 kilohertz. And so this compares rather nicely for a trap of that size. And what it actually means is that if we have to switch off cooling during clock interrogation, the increase in second order Doppler shift is on the order of 3 times 10 to the minus 20 per second for indium. And even for the much lighter aluminum, it would only be on the order of 1 times 10 to the minus 19. Next, I want to talk about micromotion. So we're worried about residual RF electric fields at the ion position, which give rise to both a second order Doppler and an AC Stark shift. In the case of indium, the second order Doppler shift dominates by more than an order of magnitude, so I will use this in the following to quantify the results, although they, of course, similarly apply to AC Stark shifts. So again, this is a contribution that's above 10 to the minus 18 in all published error budgets. And so the natural question is, can we improve upon the determination of micromotion amplitudes? We're also particularly interested in that because we want to trap axially extended crystals in a segmented trap. And so we're particularly worried about axial RF field components. And this is actually a major design consideration for our traps. And of course, we need the experimental means to measure this. So we conducted a study of 3 methods to see whether they're capable of compensating to below 10 to the minus 18. At last year's IFCS, Tanja Mehlstäubler already presented some of those results. So this time I only want to concentrate on something we found afterwards, which concerns the resolved sideband method. Just to quickly introduce the method, it's as simple as it sounds. We use a narrow transition to probe the phase modulation spectrum due to the micromotion, and from the relative peak amplitudes, we deduce the micromotion amplitude. So if we radially displace an ion from the RF node, this is what we would expect to see. However, when we did the measurements at Doppler temperature, they look like this. So there's some offset in the 10 to the minus 19 range that wasn't expected at first, because looking at the motion of an ion with compensated micromotion, there is no component at omega RF in the spectrum of this equation. And the answer is phase modulation comes from this term, and one is usually used to truncating this after first order in the Lamb-Dicke regime. However, the lesson here is if you look close enough, at some point the nonlinearities start to show up, and they mix these 2 components down to a sideband at omega RF. I had some animations for people more comfortable in the time domain. Unfortunately, they don't work, so you have to use your imagination a bit. So as the ion undergoes secular motion around the RF node, micromotion changes its phase, and so does the sideband Rabi frequency, and that means that the population that builds up during the first half of the secular period goes back down to the ground state during the second half. And so one would expect no population to be measurable. However, if one also takes into account the correlated phase modulation from the secular motion itself, then this partially prevents this cancellation. And so over time, there is a population buildup in the excited state, and this is what we actually detect. We can also do this quantitatively. So for a Fock state, this is the signal one sees, where the Q is the material Q parameter of the trap, and eta is the Lamb-Dicke parameter. If I plot a thermal average of this sideband strength as a function of excess micromotion amplitude, then this is, of course, a constant contribution. Now, if we add excess micromotion to this derivation, we get this second term here. And the good news is those 2 terms are in quadrature. So the overall measured signal will still be minimized when excess micromotion is compensated, although there is this offset here. And if we cool further down, this offset becomes smaller until finally in the ground state, basically, we measure the excess micromotion signal. And we've done this experimentally, and we indeed see that for lower temperatures, this component decreases until finally in the ground state we don't see a sideband anymore. What this means in terms of the micromotion resolution is that if we do those measurements at Doppler temperature, this effect limits us to about 2 × 10⁻⁹ resolution. And I just want to stress here that we're not using very unusual trapping parameters, so there are some single ion clock setups out there that might see this effect as well. Just for completeness, the study also included a new model for the photon correlation technique that allows quantitative evaluation in the regime where the derived frequency is comparable to the transition line width. And with this, we could compare the methods qualitatively, and we saw nice agreement. Here's a summary of the resolutions we've achieved, and the bottom line is for all tested methods, we could compensate to well below 10⁻⁸. And all of these results have recently been published here. I mentioned earlier that we're worried about axial micromotion, and these are very new results from a trap we just put into operation, and it looks promising. So it looks like we have a range of about 300 microns where we can store an indium ion with a second order Doppler shift due to axial micromotion below 10⁻⁸. So finally, I want to talk about the black body shift. I've mentioned earlier that indium has a low sensitivity to black body radiation. However, this still amounts to 10⁻⁷ at room temperature. And so we also need a low uncertainty of the thermal environment that the ion sees. We've taken two measures to, so the concern here is RF heating of the trap wafers. So we've taken two measures to reduce this. First of all, the trap is made from aluminum nitride wafers, which have low dielectric losses and a high heat conductivity. And second of all, we also collaborated with CMI to get a thermal model of our trap, which in combination with PT100 temperature sensors on two of the trap wafers allow us to deduce the thermal environment that the ion sees. So here's an example. This is a thermal image of our trap with 1 kilovolt of RF applied. And we've reproduced this situation by applying DC heating to the PT100 resistors, and thereby could deduce the RF losses and the heat conductivity and incorporate those into the model. Here's an image of one of the PT100 sensors. It's shielded against RF with these capacitors and calibrated to within 30 millikelvin. And we saw that it nicely agrees with the IR camera measurements, so there seems to be no RF pickup issue here. Again, these are results from our recently, from the trap we recently put into operation. And at the voltage of 800 volts where we usually operate, it heats less than a Kelvin. If we extrapolate this to where we eventually want to operate at 1.6 kilovolts, which would be 1.5 megahertz for secular frequency for indium, we still see that the trap heats less than 3 Kelvin. And our model tells us that this corresponds to a temperature rise of about 1 Kelvin seen by the ion, which would correspond to a 2 × 10⁻⁹ BBR shift. Which makes us confident that we could reduce the black body radiation uncertainty to the 10⁻⁻20 level. So that's all I wanted to talk about. To sum up, I've talked about our approach for an indium multi-ion optical clock. I've shown you how in a prototype trap we've achieved heating rates below 2 phonons per second. I've shown you results from our micromotion compensation study that show that we can compensate to well below 10⁻⁸ with different methods. And finally, I've talked about our thermal model to deduce the black body shift at the ion position. Yeah, this is the team working on this project in Braunschweig, and this is where the funding comes from. Thank you.